Good morning, everyone. How are we doing? Good to see you here, KP, Sierra, Michelle. How's everyone doing? My gosh, we have 1 week of class left. Good to see you here, Shreya and Jessica and Gustavo. Everyone is here. Meet is here. Who all is here? Say hey in the chat. Let's wake up Mewbot. Mewbot should be awake right now. 100 points. Super great. That's awesome, Jessica. So good to hear that. What are we going to work on? Canvas content, my Pearson, you name it. KP, good to see you. Nolan, good to see you. Can we do the golf question for my Pearson? You bet. Is that chapter 14? That's the mean, right? Because it talks about, like, golfers have a driving distance of something. We're going to need the formula to calculate a confidence interval for the mean. That's what we need. We're logging into my Pearson golf question to begin with. So, Stat 201. Chapter 14, golfers, and confidence intervals. Gonna get 2 cavities filled today. Had my x-rays done yesterday, and get 2 cavities filled today. Just a little, it's gonna be fun. It's gonna be so much fun. That's what I call it. I get cavities filled for fun. Oh man. I'm confused about upcoming assignment, like how to start. Yeah, we can talk about that. Been there, done that. Yeah. Don't be there, do that. Don't take good care. I take pretty good care of my teeth, I would think. Yeah, no worries, Noah. It sucks. Hey, what's up, Sam? Can you go over the using categorical variables in Caret? It says that you need to scale first before you convert them, but it won't let me look at the correlation without converting the categoricals. Yeah, we talked about converting some categoricals, and also maybe the critical value for the T. Yeah, I love that one. We'll do the critical value for the T. We'll do the golfers. Chapter 14, critical values of T. And last problem about transforming from the 474 exam. Yeah, BS 474, transforming values. And some people have asked and gotten points back. So if you feel like you did it right, let me know. Transforming values and then converting categorical. So we've got a list of things right here. Start with a little, can we look over at probability when asking about z-scores? Which one? Can we look at probability when asking about z-scores? Which one, Nolan, is it? Which, because z-scores are going to deal with proportion intervals. Are you talking about like percent confidence and like a z interval? If we could do one of those. Can we do one of the clustering questions with complete linkage from the exam? Oh, we could. So BS 474. But the thing is, with the values, with the thing, transformings is good. With that question right there, we could, Noah, but that won't be on the final. Woohoo! Not on the final. So what are your thoughts on that, Noah? Should we do it still? I'm pulling up the confidence interval question. So we could do it. It's not on the final, though. So we don't have to worry about that anymore. When the notation looks like probability of z less than, sure. So let me put that on here. We'll do some stat 201. They'll switch to 474. So stat 201, z-scores. Yeah. Okay, yeah. Ask me on Discord, and then I'll send an example, and I'll talk about the mathematics on it. Thank you, Noah, for asking. Oh, 100 points. Yes, transforming is still very important, though, like the idea of transforming variables. So, a great question. Z-scores and finding probability above or below. Okay, we got a list of stuff. Let's go find that golfers question. I've almost got it up right here. Thank you so much, everyone, for being here and all those questions. We got 5 questions. 5 questions. This song, I like this one too, yeah. I actually just found the T-score one. So let's do the T-score one first. And this is actually very similar, Nolan, to the one you asked about. Can you go over confidence rolls for the mean, homework, hot dogs, and sodium? Let me throw that on here. Stat 201, chapter 14, hot dogs and sodium. Can you go over test, trial, and model comparison? Yeah, BS 475. Test and model comparison. I was actually looking up stuff from the class yesterday, Shreya. Here we go with the first one, the critical values of the T for stat 201. Let's jump into it. Here we go. Okay, does anyone know what we're gonna need for T-scores? Oh my gosh. Does anyone know what we need for T-scores? Can anyone help us out? Hannah, good to see you here. Does anyone know what we need for t-scores? What do we need for t-scores? Well, kind of. No, a good answer. So a t-score was developed by William Gossett. He worked at Guinness Beer, so true story. He came up with the t-score and published it under the name Student because it was a pseudonym. So William Gossett invented the T, which is basically the Z. Now you have to use T's when we're doing the mean. I like to say Mr. T is mean. I'm sure he's a nice guy. But the t-score is for means, which is quantitative data. So we need a t-applet. Now you can kind of guess these. I'm going to show you how I can kind of guess them, and then I'm going to show you how to get the answers. Now, if you're taking the quiz right now, don't actually guess them. You could take some educated guesses. I'm going to explain briefly how I know this. I know what the z-score is for 90%. It's 1.645. The z-score is always that for 90% confidence because I've been doing this a while. So no worries. No, z's are like constant numbers that are always like a certain value. But the T is based on degrees of freedom, as you can see there with the DF. So when we get the T-score, we can take a good guess from the Z, but we pretty much need to look it up. Go right there, Shreya. We need to know the difference with the Z does not have degrees of freedom and the T does have degrees of freedom. So since I know the Z is 1.645, the T is always wider. And let's actually show that right here. So we're going to pull up the T curve and show how the T is always wider. Now remember how I said the Z-score is 1.645? Well, watch this. We go to the between and we put 90%. But if you go to high levels of degrees of freedom, what is the t-score? At a very high level of degrees of freedom, the t-score will equal the what score? Remember what I said the z-score is? With a lot of degrees of freedom, the t-score will equal the what? When you have a lot of degrees of freedom, the t-score converges. It actually goes when you get infinite degrees of freedom, but there's a slow convergence towards the what? As the t gets more degrees of freedom, the t will converge towards the what value. What value does this converge towards? So the t converges towards the what score? The t converges towards the what? The z-score is Meath. You got it right there, 100 points. The t converges towards the z-score. So that's how I can take educated guesses at these. Since I know the z-score for this, I can kind of guess it a little bit and be like, okay, it should be about 1.74. And this one, that's going to be about 1.99. And we got them both correct. Now let's show how to actually get them right here. We're going to make a smaller version on the screen. Do remember the t-score is on the screen right here, or the t-applet that I'm using. So you're going to see a smaller version over here, and we'll show the answers. So hopefully that is still viewable. I think that's readable. So we go to the between, and we put our 90%. Now with 90% right here, we need to put the degrees of freedom equal to 19. So now it tells me 1.73. So this is the answer to the question right here, and I was lucky enough to get close enough that it gave me the answer by decimals. So 1.73. And if you're solving problems, make sure to carry all the decimals while solving it. 95% confidence means to shade the middle 95%. This is a z-score is 1.96, degrees of freedom 88, and it's 1.99. We got that one exactly. Does this make sense right here, what's going on? The T is kind of like the Z, but it's based on degrees of freedom, which for a one sample T is n-1. So it's kind of like the Z-score, and you have to use an applet usually to solve it, or you can kind of deduce it. Now, what's really, really great is if you hop over to our upper level classes, we actually don't have to worry about solving what the t-score is by hand. We would just simply go right here and do the following. We'd do t.test and do something like empty cars and do this, and it automatically does the work for us and creates the 95% confidence interval. So this is kind of how we do it in upper level classes, is we don't actually have to go in and solve the degrees of freedom and get the t-score. That right there is a t-test, actually. That is not the t-score for the interval. But it does all the work and makes the 95% confidence interval to say, I am 95% confident the true mean miles per gallon of these cars is contained in the interval 17.91 to 22.26. So knowing how to interpret this and use this comes into play in later classes where we can just run t.test, and then it gives us the answer to the question, gives us the interval, runs the test. We can also go right here and do something like mu equals 20, and it changes what the t-test is now. Changes the t and the p-value for the test. So then you have to know what a test is, and you have to know what a test statistic is, and you have to know what a p-value is to interpret what all this means. Any questions about this problem? A little kind of peek into what the upper level classes use this for, but the understanding about how t's are like a z-score, and how to find the t statistic with a certain degrees of freedom and know what's going on. Any last questions about t statistics here, degrees of freedom? Any step 1? What questions do you have? Can you go project 2? Yeah, we can try to do that. Project 2 is it due this weekend? I'm trying to think of the due date. I have a lot of due dates fluttering around in my head. We might have time to do some project 2 today. If not, we'll start tomorrow with it. Project 2. If we don't get to it today. Yeah, no, good question right there, Jessica. Yeah, using the applet right here, if you're doing confidence intervals, you want to do the between because that shades the middle area. You can also do it from the normal curve. This is my favorite applet to use for this. It's just a very good visualization. And then you would go to the between. Where's the between? Yes. Nope. No. Is this it? That's it. They might have changed that recently. It looks a little different to me. And that would be like a 90% conf roll. No worries, Gabrielle. Thank you for asking. We might be able to. What day is the project due? I feel like it's due on the weekend. I want to make sure we do a good bit of streaming on it and good bit of advice because I want people to do really well. I know some people had a little lower project 1, but look over. My best advice for the project right now is look over the rubric. The rubric's going to walk you through step by step, like what you'll be graded on. The grader literally clicks the button in the rubrics. I was working on the group project for 475. Do we need to transform the summer contest data into a TISBL? Yes, you do. Yes, you do. Dylan, good work. That's the first task. The data is definitely not in a TISBL. Took me 5-ish minutes to do that. I worked through it, found some pretty decent models, and I saw how it predicted on the answers because I have the answers. And this is real data. I'll probably tell everyone what it is afterwards, but you're actually using real data. So Dylan, you are 100% right. First task is getting it into a TISBL. So it is, think about how you will put the year month, big hint right there, and get it indexed. So you need to think about the index. There's no keys on it. There's just a measured variable and an index. So nothing too crazy right there, but I think you can do it. It's go look at the TISBL section of the book, chapter 2, I think. Great questions, Dylan. Let's have her do another question. Can we do more on the predictive demand homework assignment as well? Yeah, Shivam, we'll be doing that here soon. You bet. We're going to do a little 201. We got that on the list. Thank you so much, Shivam, right there. Let's throw some points out. We'll be doing some predictive demand. Dylan, great questions right there. We're going to do some golfers and confidence rolls next. And so we're going to have to actually find a T statistic for this. There's the 1,000-chip trial one. Here we go. We got the golfers question. Can we do the 90% confidence roll flight question? Yeah, I think we can do it pretty quick. Let's do that. We're going to be doing lots of questions. 90% confidence roll flight question. Chapter 14, 90% confidence roll or flight question. Flights. Okay, it's time for the golfers. First and 5, do we do the initial step for the project? When I did initiate on 3 and step 1, it took way too long. Yes. That's the thing, Sierra. That's the thing. You might initiate way longer. That's going to be the issue. So for the project, you have to watch out. I've had people say it took like an hour or 2 to run. I've had people who've run it overnight. This is the real world handling of code like that. So Sierra, so it's going to be a little bit of fun with that. It's going to be a little bit of fun because, like I said, these kinds of things we weren't able to do 5-10 years ago. So with the project, these are things that are going to be like, well, how much computing power do we need? I had students thinking about sending it to like ORNL supercomputers to get it done. I've had some interesting ideas for how to handle the data and work with it. So Sierra, maybe change the initialization. Do this, go to a very high initialization, which is a bad idea, and then start moving back the initialization to see where it starts to really get your computer really slowing down. But that's just a really good validation right there of your model. Maybe wait till you're on your final model. Awesome. Real world data, real world problems. Oh, I love it. Yeah, no, there's no exact number. I would probably, because the initialize just really, do I still have that graphic up? No, I put it down. The initialize is where it is initializing at. So I would have it initializing way later in the series. Good question right there. Wait, let's do a cut in the video. Cut in the video. Gonna get the right time for the question. Okay, so we got 57. Here we go. Can you find the p-value? Yeah, let's find a p-value here. Cooper will do that in a moment. You got it. Here we are with a 95% confidence interval. We are given the summary statistics. So if we want a 95% confidence interval for the mean, what do we need? If we want a 95% confidence interval for the mean, what do we need? Assignment 6, the goal of the project based on the domain. Correct, Yakui. You got it. If we want a 95% confidence interval for the mean, what are we going to have to find to do this by hand? What are we going to have to find? If we want a 95% confidence interval for the mean, what are we going to have to find? What do we need? Let's take a look. So we were just talking about this a moment ago. To make a t interval, we need y bar plus or minus t n minus 1 degrees of freedom. That's subscript. We don't actually times it by that. We put a little star on this, meaning you pick it based on level of confidence, and then s over square root of n. Now, good for us, we have n, we have y bar, and we have s. So what do we need right here? What do we need that we do not have right now? What do we need to solve this that we don't have? We're missing a value. What value are we missing? What value are we missing? We're missing t. So the t is the t-score that is used to give the level of confidence. And we go over here to the t-applet. It's going to be 1.97, I believe. Probably about 1.97. Now, if you're wondering, how do I know that? The reason I know it's 1.97 is, well, first off, what are the degrees of freedom? There were 202 golfers. So what are the degrees of freedom? Degrees of freedom for a one sample t is n minus 1. Degrees of freedom tell you the shape of the t-curve. So if it has very little degrees of freedom, it's smashed down. If it has a lot of degrees of freedom, it's very high, like the normal curve. So what are the degrees of freedom when we have 202 sample? For a sample size of 202 for a one sample t, so remember the degrees of freedom formula for one sample t is n minus 1. Jessica got it there. It's 201. It's probably about 1.97. And the reason I know that, there it is right there. How did I know this? Because this value is very close. Put one letter in the chat. This value, because of the high degrees of freedom, 1.97 is very, very close to the what score? It's very close to the z. Great job, Sherry, right there. It's very close to the z. So we now know the t-score is 1.97. And make sure to use the t-score, because if you don't, you will get the problem wrong. It's 1.972 to be exact. Degrees of freedom are subscript. This just is telling you which t you're using. You don't actually plug that into the formula. So now we go here and take y bar. And then we multiply. There we go. Just comes down to a make sure you put everything in the calculator right problem. When you're doing this right here, make sure to do 8.2. Oh, wait, first you got to square root. And then, oh my gosh, 8.2 divide by, there we go, that's this, times that by 1.972, and that's the margin of error, 1.14. I like to express my intervals as the margin of error in the center. Every interval can pretty much be expressed this way as a symmetric interval where you have the margin of error in the center. The center would be right here, and then the margin of error is the plus or minus. So if we use this information right here, we could go back to our problem and make sure we put this in correctly. So incorrectly. So 286.6 is the center, plus it wants one decimal, so, well, 1.14. So 287.7. And you got to type it in right. If you don't type it in right, you have a problem. And so 286.6 minus 1.114. Did I put that other one in right? I feel like I made an error. 285.5. Just going to check that other one because I feel like I entered an extra decimal or something. 286.6 plus 1.14. No, we got it right there. Cool. Bunny's in the chat. So interpret what this interval means, or wait, interpreting the interval raises some problems. Yes. So what they did right here for this problem is they took the mean of means, I believe. How far do golfers at a country ball drive a ball? A histogram of the average driving distance. Okay, so they took the average of the average. So the average is going to have less variation in it because they're going to a golfer and finding out that golfer's average distance because they want to know how far do golfers drive a ball, and that would be like on average for all golfers. But they're then taking a golfer and having that golfer give an average distance, and that average distance is being used to find an average distance. So this is actually what we call Y bar bar. The problem doesn't go into that, but it's a mean of means. So means have less variation in it. It's like, imagine I have you drive a ball 100 times. Well, sometimes you're going to drive it like 10 yards, and sometimes you're going to drive it like 250 yards. So your mean is going to be around the center of it. It would kind of look like this distribution here, and this is a distribution of means. A little bit confusing. I don't think we've ever gone that in detail on the test. So let's see right here. The sample is not, no. The histogram shows that the data is no. Wait, what? Interpreting the interval raises problems. The 10% condition is not satisfied because the sample is too large. No. The histogram shows the data is skewed so that student T will not work. No. The sample is not random because, yeah. So they only chose the top golfers. They need to take randomly. They failed condition 1 of random. And this is literally your random condition, your 10%, and the nearly normal condition being checked right here for you. The data are the mean driving distance for each golfer. Is that a concern for interpreting the interval? Yes, it is. Because the mean is going to have less variability in it, and they get into that right there. So the mean for each golfer is less variable than a singular observation. We should get everything right. Woo! These are just interpretation problems. We've never gone this in depth for the last one. The 3 conditions for a confidence interval for the mean are random, which means we randomly select the golfers, less than 10%, which means we select less than 10% of all golfers at the country club, and last condition, nearly normal, which means the distribution of the data needs to be somewhat normal, and this does look to be. It's pretty nearly normal. Of course, the larger the sample size, more skewed it can be. This is a sample size of 200, so even if it had some skew, probably fine to do the confidence interval for the mean. But that's got it. Good question right there. Let's do another 201 question. Here we go. We're just knocking out those 201 questions. We got flights confidence intervals next. We're going to do confidence intervals for those flights. We are knocking out 201 questions. Confidence intervals for flights. I do not like... They changed the way this looks. Bob Pearson making updates. Changing the way. Here we go. Flight leaving on time chance. Let's do it. Found the question. Thomas is a big fan of those 201 reviews right there for 100 points. Thank you, Thomas. 2350. Here we go. Next question. Okay. So once again, we get the notation for this question. The notation is very similar to the last question we did right here. So knowing what formula to use is important. Let's break down the formula a little bit more that we have. So a formula for the confidence interval for the mean works the following way. When we do a formula for the confidence interval for the mean, we need to first figure out the center, which is our best guess. If I told you we usually see about 80.44444% of flights leave on time, in the future, what percent of flights would you expect to leave on time? What would be your best guess of the percent of flights that actually leave on time? So what would be your best guess? If I told you 80.44444% of flights leave on time, and you wanted to then guess the percent in the future, yeah, Jessica, that's it. 100 points right there, because that's our best guess. The center of the interval is literally your best guess. It's like, well, I guess that's probably a good guess of the truth. But does that mean that's what will happen? No. We need what is called a margin of error. So this is what is called the margin of error right here, which gives an uncertainty. Now, the margin of error has 2 components. The first component being how confident you are. So this gives the confidence level. And the second component right here being the standard error, which is S over the square root of n for this problem. Really depends on what formula you're doing, but that is the standard error right there. So this will help us to create a confidence interval to estimate the true kind of mean for average amount of flights that are not on time. Is it not on time? Something about flights being on time or not on time. So with this right here, we need to find the t statistic because we have everything else. We have y bar, we have s, we have sample size. So what are we missing from this output right here that's going to help us find the t? What are we missing right here, which I've added to the table? So tell me the notation for what we've missed. It's not in the table. What are we missing? Rajiv, great to see you here. Rajvi, good to see you here. What are we missing? What are we missing? What are we missing from this table? I've added 71. Well, we're missing the T. Meets, great job right there. We're missing the T, but what are we missing that's 71? N minus 1, which is the degrees of freedom. So this is known as degrees of freedom right here. There we go. Excellent work, Kevin and Meath right there, and Jessica. We are missing the degrees of freedom. So now that we know the degrees of freedom, we go over here and we enter in 71 degrees of freedom on the T. Let's drop that in the chat. So we got here 71 degrees of freedom. And now we want to build a 90% confidence interval. So a 90% confidence interval will be built for this problem, which means, and you can solve it right here by going to 10% on the outside. It's better visually just to do the 90% on the inside, and that is the 90% confidence interval T statistic, 1.667. So we can go to our output right here and put T, and we have all the values. Let's go ahead and solve this right now, and we can pretty much do the problem. Okay, we're just plugging in the numbers. You don't plug in the subscript because that just tells you which T you're using. Isaac, great to see you here. And then 3.52751 over. There we go. Okay, I square root 72 first. 72 square root 3.52751. There we go, times by 1.667. That's the margin of error. I now re-express my interval. That's not how we write an 8. There we go. And now we solve for the upper and the lower. Let's find that upper and that lower. How are people doing on these problems? Are they making more sense? Tell me if I'm going too quick or too slow. We're just solving right here for the values that are going to go into the interval. The upper value is the center. Remember, we already expressed this as a center plus or minus a margin of error. And so the upper value is going to be the center, which is the sample mean, plus the margin of error, which we found by T, times S over square root of N. How are we doing? And that's the upper. And we round. And then the lower, just showing right here, 80.444 minus 0.693. Okay, awesome. Yeah, it takes a little bit of getting used to. Once again, I'll show another thing right here at the end. The good news is if you do more analytics, I got a really great message from one of my students who's in vet school. She was saying how like she helps other students make graphs and stuff. They send her data and they're like, hey, can you make a graph of this? And she's like, yeah, of course. She's like the skills that I learned. She took like 320, 474, 4. She didn't take 475, I don't think. But she took a bunch of our up-level analytics courses, and really great just message from her saying all these great things like about how she's using the skills. But oh, it's awesome. Oh, she took 207 too. That's where I first had her as a student. I don't know. Hearing from students just makes me so happy that they use the skills. I love it. Check the assumptions, independence, yes. Randomization, yes. The conditions are, we like to say random and independence are the same thing. So pretty much if it's random, it is independent. They break it apart right here on the test or in the questions. We just usually talk about random. So 10%, less than 10%. And is it nearly normal? It definitely is. This right here, other than a little bit of outliers, looks pretty normal. So once again, the conditions are random. We randomly select the observations. They sometimes break apart that into an independence portion, but if it is random, it should be independent too. So I'm fine with that. The next condition is less than 10% of the population is selected. So assuming this comes from a population of more than 720, our sample size 72 is less than 10%. And the third condition is nearly normal, which would state, depending on how big of a sample we take, 72, this distribution could not be super heavily skewed. If it was heavily skewed, we'd need a sample size of at least 100. So the more skewed the population is, the larger the n needs to be. So this is kind of a play on large enough n, but there are other ways to check the nearly normal, so it's more of a global term. Conditions, those are more of a memorization type thing. So make sure to memorize and put them on note cards. Confidence interval for the mean, random, 10%, nearly normal. Testing the mean, confident, random, 10%, nearly normal. Make sure to write those down. Interpret the interval. I am 90% confident that the true, right here, the interval contains the true mean monthly percentage of times on time. So it is on time, not late. They say we are, or we can be. I like to say I am. That's the easiest way I like to do it. And that should do it 100%. Now, once again, if you were doing this inside of R, which is my favorite way of doing things, you can literally create confidence intervals very quickly by just going t.test and doing things like iris and then running the data set you want and getting the answers for the confidence interval just like that. If you have your data, it creates like that. And I think if you go here and do, is it level? No. That's not it. Is it confidence? Confidence level. There it is. We did double equals. So you can change the confidence level like this. So hopefully, Jessica, this lets you see that we don't actually have to look up the T's. This is the T test right here. That's not the T for the interval. But if you wanted to do an 80% confidence roll, you could just run this code right here and get your 80% confidence roll for the supple lengths of flowers in the iris data set, or like the true supple length of all flowers, because I am 80% confident the true supple length of flowers is contained in the interval 5.75 to 5.93 centimeters. I don't know what the units is. But this is how we would do it in practice rather than having to find the T statistics along the way. But the understanding of what a T statistic is and calculating these things is very important to understand the mechanics, because you don't want to just have this be magic. You want to understand, okay, what's that interval? How is it created? This is the mean of the variable right here, and we could confirm that. We're going to do another question right here by just going right here and going mean, and there's the mean right there. That's the center of the interval. So, yep. And you could find the margin of error. Margin of error would just be minus the mean. There's the margin of error of the interval. There we go. Center minus the upper minus the lower is going to be the margin of error. Let's do another 201 question. Here we go. We're rocking and rolling through some 201 questions right here. Z-scores and finding the probability above and below. So let's do some Z-score stuff right here. This might be a little quick section, and then after this, we are going to have some 474 coming up right here. We might have time for more. We've been doing pretty quick pace today. Get all that energy. Here we go. Back to the main screen. Okay, so when we're doing Z-scores, Z-scores are not for quantitative data. If you're working on chapter 14, make sure to use T-scores. Check the formula you are using. You get to use the formula sheet on the test. Practice using your formulas. You do not have to memorize formulas, but you do need to know how to use them, and we will give you T-scores on the test. So if you write down this formula right here, y bar plus or minus T star means you get to pick it based on the degrees of the confidence. N minus 1 are the degrees of freedom. S over square root of n. Knowing how to find the T-score is very important. So we use Z-scores for confidence intervals or for Z-tests, which are based on proportions. So if you were to have something that said, let's do this right here. You ready? In the chat, what percent of area is greater than Z of 1.2816? Who can answer that for 100 points? So we want the percent of area that is greater than a Z-score of 1.2816. What percent of area? Or like what amount of area is greater than a Z-score of 1.2816? What amount of area is there shaded on that curve? We'll see what people say. So you want to go to the David M. Lane applet, and then you want to make the curve shaded in this way. And just understanding how to like read the curve. Right now it's not showing, it's showing this right here. Great job, Kevin. 100 points. It is 10%. Like, why did you choose such an exact number, Brian? It's the Z-score for an 80% confidence roll. So 1.2816, and we want to go to above, and there it is visually right there. Now, if you notice, Kevin, I said it's the Z-score for an 80% confidence roll, because think about this. If I know below this is 10% and above this is 10%, then that's 20% on the outside. What percent of area would be contained in here, in between here? If 20% is on the outside, then 80% is on the inside. And I've just been doing this enough that I know the Z-score for an 80% confidence roll. Great job, Shreya, right there. Now, if you didn't know the z-score, you could just go over here to this screen and go to between and say 80%. And it'll give you, it doesn't do it as many decimal places, but it will give you the z-score now. So this one we put in the, why would it be between? For confidence intervals, we usually like to do between. But these are just different questions right here, Nolan. And Nolan, let me know, since this is your question, does this help answer your question of what you were wondering about? Should I do like another one to say like, what percent of area is less than a z of 0.673? It says greater than. Which do you have a specific problem you can copy paste? Can you copy paste the problem? Is it my Pearson problem? And we can do that one. So I entered another problem in the chat. It says what percent of area is? Yeah, awesome. Find that problem. We'll do it right here. If you just copy paste it or type most of it, I should know it. There's Meath got it right there. Yep. And I guess I wasn't close enough. I was trying to do 75% Meath, but I was super close. Darn it. You got it down to the decimal right there. I was trying to do the IQR one. There it is right there. I thought it was about 75%. I guess we need a little higher. Oh, is it a 4? There it is right there. I'll have to look into that. Let me get the exact. I really want to know the answer to that. Is it this? No. There it is. There's the exact version of it. So I asked R to tell me the answer, and it's 0.6745. I'll try to memorize that better. So that is the answer right there. That is the IQR is between that. Because if 75%, my hair's just going to go crazy today. If 75% is below that, can we go over the quiz? Which part of the quiz, Vanish? There, can you do the chapter 14 sampling distributions for the sampling mean carbon monoxide? So we got the carbon monoxide, and we've been doing some of the quiz today. So here we'll put the carbon monoxide on here. Stat 201. Chapter 14, sampling mean carbon monoxide. Okay, we got hot dogs and sodium next, and we're in carbon monoxide next. Here we go. Okay, everybody, we got more 201. Let's check it out. We got hot dogs and sodium, and then we got carbon monoxide next. I got so many interesting questions on this. Hot dogs and sodium, carbon monoxide, 1,000 chocolate chip trials, yogurt, rats in a maze. Where's that hot dogs and sodium question? Wait, what? Hot dogs and sodium. Here we go with hot dogs and sodium. Let's go check out hot dogs and sodium. Let's do it. We got hot dogs and sodium right here. Get your hot dogs, get your sodium. Best quote ever. Sam will take that as a quote today. We got hot dogs and sodium. Okay, quote of the day, 265. We got hot dogs and sodium. So let's do it. Let's check out the hot dogs and sodium. Okay. What can you do it by memory right now? What do we need to identify for this problem to make a confidence roll for the mean? What do we need? Check out to see if you remember what we've been doing. This is our third one today, I think. What do we need from this to make a confidence roll for the mean? So see if you can do it from memory. Think about what you need, or I'll show you on the screen real quick. You ready? What do we need to do a confidence roll for the mean? See if you can be like, okay, we need this, we need this. This is where you check and be like, a confidence roll for the mean requires, what do we need? See if you can answer it in the chat right here while I highlight it. We're rocking and rolling through questions is what we're doing. Can you tell me what we need? Not hot dogs and sodium today. Yep, we got some 474 questions, you bet. So was KP asking about that? Standard deviation T and N. Great job. And then you wrote mean also. I didn't see that. You're great job right there. And I think Kevin also got it. Awesome, KP. We'll have it in the video. Thank you, KP, for being here. Then focus on tool, and then we'll switch. I think that helps people who come for one class. Then if we switch, and we'll switch here in about 15 minutes or so and do the remainder. Mostly focusing on 474. So why my bar is 302 plus or minus. That's the margin of error. You're welcome, KP. And then T star with n minus 1. We'll find that right here. Let's go ahead and find that. What are the degrees of freedom for this? What are the degrees of freedom for this? Who knows the degrees of freedom? See if you can find the degrees of freedom. Hey, could you please clarify how do we decide the include? No zero variance true. I'm still thinking about the holiday variable on the bike data set. Yeah, you might not include that. Another good question right there. That's your own choice. You might not include it. I would just specify that in my report to say I decided to include this, even though we don't have a lot of variables. I think that could be a decision. Since it doesn't have a lot of variables, you could include it. But of course, it has near zero variance, so you could decide to not include it. You could say, due to it having near zero variance, you could decide to not include it. Remember, all models are wrong. Some are useful. There's no right answer. I love working with real data. The z-score right here is going to be 2.001. And let's show that a little bit better. Here we go. I swear they moved those. 95% confidence is basically 1.96. You're welcome, Manola. Great questions. And so 2.001 is basically 1.96. Remember, the T is going to be further out than the Z at all times. It converges towards the Z as we get more degrees of freedom. Review the earlier part of the video to hear more about the T and the Z. But we're using the applet right here to say 95% confidence because it told us 60 was the sample size, n minus 1 for a one sample T is the degrees of freedom. And you can see it right here in the formula, n minus 1, and then the star represents related to 95% confidence. So that's 2.001, which is basically 1.96 and also basically 2. Next, we have the standard deviation. Standard deviation for this interval is 37. And next, we have the square root of the sample size, which is 60. And that is the formula right there with everything filled in. From here, we just need to go out and solve the formula. So we're just going to do 60 square root first. And then we take and do 37 divided by that. And then we times it by 2.001. And that's the margin of error, 9.56. We rewrite our intervals so that we always have the margin of error over there. And the center of the intervals here. Probably shouldn't include the margin of error right there. But now that we have our interval rewritten, we know it's 302 plus or minus 9.56. So that was 302 plus or minus 9.56. 302 plus 9.56. Copy, paste, 1 decimal. 302 minus 9.56. Copy, paste, 1 decimal. Make sure to round properly. These ones can be tricky. If you don't use the T, you will get it wrong. If you don't use the T, you will get it wrong. If you don't use the T, you will get it wrong. And if you don't round properly, you will get it wrong. What assumptions can be made? Oof, these are the tough ones. Okay. We assumed, what assumptions were made for this inference? We assumed that the hot dogs are independent and the distribution are normally distributed. Pretty sure. Yeah, because it talks about normal. So this goes to basically your random and independence condition. I just call it the random. And then normally distributed, and they're also less than 10%, which I think they get into down here. Is randomization met? These are the questions I hate. We don't know that the hot dogs were sampled at random, but it's reasonable to think they were. Yeah. Is it 10%? Yeah, 10%. The hot dogs are less than 10% of all hot dogs in the world. So yes, the hot dogs are less than 10%. Be very careful right there. Is the nearly normal condition met? We don't know, but it's a pretty large sample size. So because we can't see the data, we'd actually have to see the shape of it to know if it's met, and we don't have the shape of it. So we don't know, but 40 is a pretty decent sample size, or 60. So it's more than 40, which is pretty large. So probably. Explain clearly. I am 95% confident the true mean sodium content of the hot dogs is contained in the interval blank to blank. So try saying it out loud, try practicing it, and we have it right here. Boom. Did we get it all right? Wait, we're missing a blank. Is the randomization condition met? We don't know. This is the one I'm worried about. Woo! Those iffy ones are the craziest ones. We were on a streak on 201. I'm going to ruin that streak. But, man, scary question right there. It's like, well, it doesn't say, so we don't know, but maybe. More questions. We got one more 2-1 question, then hopping over to 474. Let's do this. As number 2 on the homework, what's number 2, Vinish, right there? Let me know what number 2 is. We might have done it. Which one is number 2? Wait, hot dogs and sodium. Dang it. Need to get the time for that. I didn't get the time for that. Carbon monoxide from sampling distribution. Let me go get the sampling of the mean. Let me do some carbon monoxide. Sampling mean. Might be this one. Oh, maybe it is. Hot dogs and sodium is number 2. We just did the hot dogs and sodium, right? Wait, didn't we just do that? Yeah, so we just did that right there. It was hot dogs and sodium. Woohoo! Good stuff. Okay. So let's hop into some carbon monoxide. I always wanted to say, let's do this. Okay. Here we are with the carbon monoxide problem. And there's a huge difference between this chapter and confidence intervals. In this chapter, which is confusing, we know the truth. We know that a certain kind of car has a mean carbon monoxide output of 3.297. And we know it has a standard deviation of 0.6. So I want to point something out. In this question up here, the notation is different than the other problems we've been doing. So notice how there is no sample size that we're using to get these estimates. Not saying from the 70 cars we saw a sample mean of this. From the 70 cars we saw a sample standard deviation of this. It's saying what is the sampling distribution that is expected. I just want to point out the differences between these problems where, I'll put it up here then. In the problem below, you are getting the sample statistics from the problem. So in this problem below, take a look at this right here. This is comparing and understanding the difference between these problems. Down here, this is the sample size. And up here, this is still the sample size right here. But the standard deviation down here comes from the sample. It says with a standard deviation. So it's saying this sample had a standard deviation of this. But up here, the standard deviation is saying, let's see, about a certain kind of car with a mean and a standard deviation of this. So these are like known quantities. So it's not saying from a sample of 70, we observe this. It's saying these cars have a mean of this and they have a standard deviation of this. That makes this sigma. That's no longer S right there. That's sigma. And we know the mean. So the mean down here was, oh, that's the, not the sample. This was the mean. It's in the same spot. Perfect. That was the mean. This was the sample. And right here, we can see that this is going to be mu. So the difference right here is up top, you have the truth for what is true for all cars. So we have the true mean and the true standard deviation for all cars. And then we take a sample of 70 and ask what could happen in this sample of 70. We're down here, we get 60 as a sample, and then we get values from the 60. Does that make sense, Jessica, on the difference between these problems? Both of them dealing with sample sizes. The one asking, what is the truth of the whole population? And then the top one asking, what might we see in a sample when we know the truth? It's more of a kind of process question to be like, we know the truth for the population. What might we see in a sample? So these are interesting, different types of questions and way to ask it. I think this is probably very confusing to be like, well, wait, what's the small difference in notation where this is mu? Well, that's because a certain kind of car has a mean of this and a standard deviation of this. They did not get this from a sample. They're saying, now we're going to take a sample of 70 and ask, what do we expect to see in that sample? Down here, we get a sample of 60 hot dogs, and the sample has a mean of 302 and a standard deviation of 37. Wow, can't speak. But these are small differences right here, which are very important to know that we are dealing with a sampling distribution problem. So the sampling distribution problem solves the following way. Mu and sigma over square root of n. So let's draw the sampling distribution right here. What would be the model? And the model is written right here. So we need to find mu. Mu is going to be 3.92. And then we need to find sigma over square root of n. Sigma is that, and square root of n. Okay, so let's write it. Normally distributed, 3.97 and 0.6. So in this problem, you can draw it out by hand, but for speed today, we're going to do it in the David M. Lane applet. So 70 square root 0.6 divided by 0.717. And now we're going to go over to the David M. Lane applet. So that value right there is the standard deviation, which goes right here. Even though this is sigma over square root of n, this is normally distributed with a mean and standard deviation with the following formula to tell us the spread of the values. So we're going to hop over here to the David M. Lane and immediately plug in these values and draw the sampling distribution. So here's the standard deviation, and the mean of it was 3.297. And there's the sampling distribution. That is what we expect when we take a sample of these cars. We expect a CO2 output of this with a standard deviation of 0.0717. And so let's look at the questions. How will this distribution look? Well, it will be normally distributed. And we see that on the screen right here. It's normally distributed. And that is just the kind of rule for what happens to this distribution. It will follow a normal curve. And just want 3 decimals. Cool. And that's going to round to 2. And we get to check them. Yay! Good. Homework lets you check it. And then it says, what is the probability of a car having between 3.4 and 3.6? Now, 3.4 is going to be over here somewhere, and 3.6 is off the curve. So 3.4 is right about there. So it's going to be about 8% or so. So between, I said about 8%. There it is, 7.54%. And let's go back to it. So round to 3 decimals. Could we have gotten if we did 8%? Could we have? Nope. That guess would have been wrong. Would have been close. Would have been close, but wouldn't have gotten it. This one you can actually guess right here. It wants the top 1% of cars, and we'll show how to get this. It says to only 1 decimal, but you can guess that one because of the granularity of the answer. So to get the top 1% of cars, you'd want to go over here to the following and put in the values you found, 3.297, the mean and the standard deviation, and go to the top 1% of cars and then round that. We got a little lucky right there. It rounds up to 3.5, but that is the top 1% of cars would be expected to have a CO2 emission of 3.464, which rounds to 3.5. Any questions on this problem? This was a tricky problem. The biggest part about it is drawing the sampling distribution, and you could draw the normal curve by hand, but what are people thinking? Can you explain the last part again? Oh yeah, sure. So for the last part, thank you, Nolan, for slowing me down right there. The last part, when you have this curve, you want to click on the second button and put in your mean and standard deviation. So this is the mean of the curve, and this is the standard deviation of the curve. Let's show those over here. So you're going to put the mean into the mean and the standard deviation into the standard deviation. Does that make sense right there, Nolan? So take the mean and it goes to the mean. Take the standard deviation, it goes to the standard deviation. Does that make sense right here? So this value is this value right here. Here's the mean, there's the standard deviation. Okay, cool. Now that we have this in the applet, we want to ask the top 1%. And the reason it asks this on the question is it says, there is a 1% chance that the fleet's mean CO2 is greater than what value? So when you look at this visually over here, there's a 1% chance, because I put in 1% right here, that the CO2 level is higher than this. So you want to go above and put in 1%. So there's a 1% chance that the CO2 level is at or above this, and this rounds to 3.5. So that's how I got the 3.5 answer I got, was knowing that, kind of knowing where it would be out on the curve, but 3.464 rounds up to 3.5 when you round to one decimal. Does that make more sense right there, Nolan? The applet would help us solve this, but we could draw pictures on the test, or we could show you pictures. So understanding, if you're preparing for the test, what this is showing you, it's showing the top 1% of CO2 output from cars. So from the fleet of cars. Are the only ways to do B and C to use the applet? Kind of. So on the test, we oftentimes like to give values like, what percent of time would we expect? So here's a very good way to do a test question. Ready? What percent of time would we expect 70 cars to have a mean above 3.369? Okay, so what percent of time would we expect 70 cars to have a mean above 3.369? Let's write that down here for people to see. And I want you to notice something about this and why we could solve this without the applet. So why can we solve this? Who can help explain why and how can we solve this? In 474, Z's and T's come into a lot of use. So what percent of time would we expect would 70 cars to have a mean above 3.369? I got the answer. What do you think it is? It's Nibbles Day. What would it be, and how would we know that? Do you notice anything about 3.369 and why that would be something we could solve? We'll give it 30 seconds right here and see if people come up with an answer. Okay. What are your thoughts? One more chill one. Why can we use that value? Is there something about this value which comes in a lot of use? So think about how that curve right there might help us. How we could look at it and be like, oh, that's this. That means this. Think of the empirical rule. Does anyone know? What is the z-score of 3.369? It aligns with a z-score of positive 1, right? So if it is a z-score of positive 1, what percent is between there? Well, it's not quite the same. It's right. It's a z-score of 1. Good answers right there, Nolan. Good practice. It's at a z-score of 1, which means it's one standard deviation above the curve. So let's write this right here. Ready? We're almost there. So this has a z-score of 1. One standard deviation above the mean. Okay? So would you be given the curve? You could draw it. You could be given it. Like Canvas content's the best way to know what the test looks like. So you could be given it. You could have to draw it. We could expect you to find that it's one standard deviation. Turning things into z-scores can help. So it has a z-score of 1. So what percent of area is between -1 and 1? So what percent of area is between -1 and 1? Sorry for being quiet, trying to multitask. Oh, no worries, Noah. You're fine. 68%. Great job, Meath and Jessica right there. So what percent of area is above 1? So Jessica and Meath right there point out that between -1 and 1 is 68% of the area. So if 68% is between, then 32% would be on either side. So above this would be 16%. And that's the exact answer right there, but basically 16%. Does that make sense? That's some of the harder problems, understanding and connecting the ideas that we've had and we've built with the empirical rule. Is important to understand that this is just a z-score of 1 right here. So we could literally go back and revert the curve into z-scores and show that above 1 is 16% of the area right there. Does that make sense? Let me know. But that is how we could do test question related stuff. Oh, cool. There you go. One of my colleagues has been on a road trip. Does that make sense, Nolan? These are some of the tougher questions. Without the curve, how would you know it is a z-score 1? How can we get a z-score? Good question. So we can always draw the curve. So what you could do is if you have the mean and standard deviation right here, 0. You could go down here and draw your curve out. This is one way. So we're going to take the curve right here and just draw it for a moment. This is one option. I highly suggest this. A lot of times I've seen on people's scratch sheets of paper that they draw the curve and they put the mean and then they go up the standard deviation right here. So this is the amount we're going up by right here. This is the center of the curve right here. And so they would get 3.369 when they go up 0.0717. Additionally, we could find the z-score for it by doing observation minus the mean of the curve over standard deviation. So the observation is 3.369 minus, I'm going to block the screen right here. You're welcome. These are good questions right here. And that would equal a z of 1. So all of these ways right here to either draw it or to do observation minus mean over standard deviation, just using a version of that where we're observing this. This is the mean of the curve. So the observation would be this right here. So observation minus the mean of the curve over the standard deviation turns something into a z-score. So all of these ways right here are good ways to see that it has a z-score of 1. And once we know that, we know we're on the empirical rule. And we could kind of go in and say, well, between 1 and -1 is 68%. And thus outside of it is the symmetric remaining 16% on either side. And those sort of solves right there. Will we be doing lab in class? You bet, Audrey. We'll be doing some lab. Let's hop over and do some 474. Woo! 201, excellent work. It's time for some 474. We had a question about transforming values, and we're going to do some converting categoricals. Transforming values. Okay, let's head over and talk about transforming values. Okay, so question about transforming values in 474. Now, log 10 is probably one of the most powerful transformations there is. You have to watch out, especially the way the questions are worded. I highly suggest, yeah, no worries, Jessica, great job. And if you're stuck on any, let me know. I've got videos for almost everything. I don't try to say, hey, here's just a video for it, but usually it's a big help. Let me know when you're stuck on stuff, and I can send, like, if I didn't work a problem today, I probably got a video for it. So I try to do a bunch during office hours. Okay, what if we have a value like 45 million? Can we talk about assignment? Yeah, sure. KP, what are you wondering? If we have 45 million right here, now there's two ways of asking this. If we collect this, it's 45. Two ways to ask this. So if we collect it as 45, what is the log 10? So like where to start in the first step? Yeah, well, we got it. We're going to be doing that here next, I think. And basically, you're going to start by getting the data ready. And I'd probably write about that in my report, how we prepared the data. So if we have 45 right here, what is the log 10 of 45? Well, it's got to be something between 1 and 2. It's probably about like, I think how log 1.4 maybe? No, I don't know. Logs are interesting. It should have a gradual, maybe 1.443. I don't know. Let's go find out. So log 10. Oh, Gustavo got it right there. There it is right there. Whoops, I did log 10 at 10. So that's the log 10 of 45. But if we do it as the millions, it's going to be this basically, and that's interesting. So it keeps the same properties. That's how log 10 works. It's really interesting. I love looking at how numbers work mathematically, but log 10 really just pulls in those extreme values. So the way the questions were on the test is we were looking at, it's already been kind of converted to in millions. The value is like, if someone says 45 and meant 45 million. If you believe you got these questions correct, let me know. I can look over it. So anytime you have questions on the test, I've already talked to a few people, made a few adjustments. But please, please, please talk to me. Or if you feel you were graded unfairly, please let me know. It's my goal is to treat everyone fairly, which is the hardest thing in the world as an instructor. It's like everyone has to be treated fairly. It's so hard because life's not even. Life's not consistent between individuals. So I hope that helps explain kind of with the log 10. Depends on how we talk about this as 45 or 45 million. If 45 million has already been talked about as 45, then when we log 10 it, it's going to be on a different scale. So watch out, because if you look at the way the histogram is built, especially for the test questions, it's built on the values already kind of being converted down from being like 45 is no longer 45 million. It's just like 45. So interesting stuff right there. Let me know if you have questions or you feel like the question was not clear. Let's head back and do a little bit with the assignment. Here we go. Okay. For the exam, would you use 45? It was, I believe, 45, correct? Because the histogram already had like -2 to 2. Does that make sense, Gustavo? Let me know if you have a question on it. The last exam in tool 1 is not cumulative, but it does have tools and techniques, Hannah. Good questions right there. Gustavo, if you want to know, let me know and I can look over your test. The histogram for the movies went from like -2 to 2. So when you think about it, it's already in millions of dollars, because -1 would be $100,000, because that's not 0.1. When you convert it, it's not $0.1 was earned, it's $100,000 was earned. Does that make sense, Gustavo? It's like you had this like bimodal shape where there was like a center around -1 and a center around 1-ish, 2-ish, and so it was already converted into millions of dollars. So converting back, and if you got something like 2, that would mean 10. Now 10 then means 10 million. And if that was confusing, let me know, because I can see data can be confusing. Let's talk about handling data right here and how to work with it. Let's work with a data set. Okay, handling data for your assignment. Converting categorical, getting started. Let's call this getting started on assignment. Okay. Let's do it. Here we go. Okay, so a lot of the code we're using is in the slides. So I'm going to be working with a completely different data set. Isn't log 10 1.3 of... it should be. But wait, are you saying converting back? Isn't log 10 of 1.3... Is there... No, you might need to message me. Is there a specific one you're wondering about from the test? That looks correct. But it depends on what the question... You might need to message me and I can look over it. It was the last one? Is the last question on the test? Let me move that real quick right here. 2 seconds. Got to pull that up. And then we'll do a little... 15 minutes or so work on getting started on the assignment. Quizzes. Okay, one moment. It's the last one you're saying. The last one. A little more chill music right here. Okay. The last question reads, the next Avengers movie was predicted to make $1.3 billion. So what is the corresponding log 10 of this transformed value? So what is 1.3 billion? So what is 1.3 billion? So what is 1.3 billion? So like, what is... So there is... Someone argued for an alternative answer to this question. It can be that in millions. So it can be that in millions. A whole lot of money. If you got the alternative answer, please let me know. I might need to check too. I had a student who already argued for an alternative answer to this one. So depends on how we express it. And that's kind of what we talked about with them. And I accepted the answer. So 1.3 billion... If you're expressing it in millions, then it would be, I wrote, so that is how to express it in millions. So that is, and so Yeah, so Gustavo, let me give you the points back. I need to probably look over. I need to put that in my notes to go check that. That's what someone argued, and I was like, yeah, let's do it. Because that is what the original histogram shows, so I need to probably look through. Let me give you points back, Gustavo. What do you think the other possible answer is? What do you think the other possible answer is? Yeah, I need to probably go look at all these and give everyone the points for that. What do you think the other possible answer is? Yep. I think that's a fine answer. So it'd be 9. Great job, Sydney, right there. Yep, the other answer is 9. 9 or 3 would be the right answers. 9 because basically it's how many zeros there are. So if we express it in terms of log 10 of millions, then it'd be 3 if we express it as the original number. But in nowhere do we use the expression of billions because everything else would not be scaled properly if we just take 1.3 and log 10 it. So you have to watch out because the context of how much it is matters right there. So I think 9 and 3 are both correct answers. I need to go through and look. I'll try to do that. Let me put that on my list to do. Check last problem 474, and give points back for 3 if someone answered it. Awesome. So we can go through and do that for everybody right there. So Gustavo, great job mentioning that, and we'll get points for everybody. Awesome. Let's talk a little bit about getting started on the 474. Here we go. Okay, so getting started on the 474 assignment. The number one thing to help out to get started right here is going to be the notes. Make sure to use the notes. Let's pull up a data set. Okay, so we got survey 10, everyone's favorite. What is a problem right now? Before we run any of the algorithms, what is going to be a problem with the survey 10 data set? What is going to be an issue when we run the survey 10 data set right here? We should probably do some of the checks on it. Let's find out. We got factors. We got a bunch of stuff right here. So let's go ahead and pre-process our data. This is the getting started. Let's run the near zero variance on it. We'll have to load up Caret. Make sure you have Caret installed. A lot of these, you can just copy paste the code from it. We're not going to use the launch data set, but we need to jump into here and take survey 10, drop it in, near zero variance, and there we go. Let's just go to the near zero variance. That should run it. Oh, that's awesome. I think, yeah. And I think we've done it. Well, what does this mean? Can you explain what near zero is? So good question right there. So zero variance is something like this. If I ask you, how many, I also have trouble figuring out a near zero variance question or a zero variance question. Like, how many tires does your car have on it? Answer in the chat right now. How many tires does your car have on it? It has to be a working tire. It can't be in the trunk. How many working tires does your car have on it? 4. So the reason this is going to be zero variance is if we're all answering 4 right here, then this is what is called zero variance. But then let's say somebody has a interesting sort of a truck with some super back wheels or something, and their car has 6 tires. So no longer, look at the data now that we've entered, it's 4, 4, 4, 4, 4, 4, 4, and then someone entered 6. So no longer is it zero variance, it's near zero variance. Variance is a variation in data. So when there's zero variance, all the answers are the same. So a zero variance vector would be something like, and we could add it on right here. If we go to survey 10 and we store into zero variance, and we store into it 5, now we should get, there it is right there. You see the zero variance? That is true that it has zero variance because why? Why is it true that that last vector in the data has zero variance? I want you to look at it. Why is it true that the thing I created called zero variance has zero variance in it? Do you see it? How all the values in zero variance? It's a numeric vector called zero variance. And if you look at it, everything they're all 5. So there's no variation. That's what zero variance means, is there's no variation in the data, which is completely useless. Rock? It doesn't matter. So then we have what is called near zero variance. Now to make a near zero variance vector, near zero, we need to go 5, and then we need to go to this thing right here, and we need to store something that isn't 5, like 10. And now when we run it, oh, did we not make it? Oh, we didn't look at this. There we go. So the near zero variance has near zero variance. If you look at this right here, near zero variance is now true for this. It does not have zero variance. The reason it has near zero variance is because there is a value that is not, or it has variation, I should say. There is a value that's not the same. So the near zero variance pretty much has no information in it, but the zero variance has absolutely no variation, no information, no variance in it. Does that make sense on the idea of these? Now, you want to generally remove these out because they just kind of clog up your algorithm. They're not going to help you. To people's questions, it was asked earlier, should we remove them? Yeah, probably. You don't have to. Maybe. Maybe. Awesome. Thank you, KP. Doing an example right there hopefully helps. I'm going to reload survey 10 and destroy those variables I created. Now, next, now that we know there's not zero variance, we could look for linear combinations of variables. I think that's the next thing we can take a look at. There's the zero variance, highly correlated. So this is going to tell us if we have highly correlated values. So let's go ahead and take and run this and see. X must be numeric. Oh, yeah. I guess let's convert categorical first. 2 seconds. All right, let's convert categorical. Where's my convert categorical? Here it is, convert categorical. Okay. Let's convert the categorical. And there's the function. And that did it, it looks like. Let me make sure. Did it overwrite? Didn't do it. I don't see the output. Do we have to store it? Survey 10 new. There it is. Cool. Okay, we got it. If you look over here at the survey 10 new, what do we have with survey 10 new now? Can I convert yes, no to 1 for our assignment? Well, that's what we have with convert categorical. Take a look. Now we have someone right-handed. Are they left-handed? And are they handed ambidextrous? So you can actually find the ambidextrous-handed people right here. Yeah, it does it for us. Exactly. We're not going to sit down and have to write all this code. Now you have to be careful because if you have categoricals with lots of levels, this can be insane. I kind of already knew that this data set didn't have tons of levels to these categorical variables. So I was kind of okay to be like, okay, I can convert this. Now you want to probably tell people about this pre-processing of data that you're doing. Like, you know, we created new variables right here for someone having a significant other no, someone having a significant other yes. And what's really going to be interesting about this, I'm pretty sure that we're going to be removing one of these columns right here. Because think about this. If you have 2 questions right here of significant other no, significant other yes, how many of those questions do you need to ask? So if you have 2 questions right here, significant other no, significant other yes, how many of those questions do you really need to ask to know the answer if someone has a significant other? Do you need to say, do you have a significant other? No. And they're like, yes or no, because that's what we have. You just need to ask 1. So due to the way this works, these are actually linear combinations. Like this is just the reverse of the other one. And this right here, there you can find out the other. So we don't need all of those. So when I run the highly correlated or linear combos, we're probably going to find that. It's probably going to be linear combos. Let's find out. Highly correlated, survey 10 new. 18 and 24. And let's take a look. Probably the code's already written to remove those. I think those are, yeah, because those are the ones we appended. So let's go back to the highly correlated. There's linear combos. Okay, so here we go, removing the highly correlated. It's just going to remove out those columns. So if you look at the code right here, which I could have probably just written myself, it's just removing the columns. So we need to go to survey 10 new and no core. So we're removing out the highly correlated columns. This is just the column space. Is this all making sense to everybody right here? I've now removed out those columns. If you take a look, exactly what I said would happen. We removed out, ooh, wait, what? We removed out female and we removed out the other one. So we didn't get this right here. Truthfully, if that doesn't come up in linear combos, I'm probably just going to remove that anyways because that one isn't needed. It says to scale before converting to categorical. So would we log and scale and then convert to categorical and then do near zero variance? It says to scale before converting to categorical. Where does it say that? Let me read that. Which slide is that on to say to scale? Yeah, this is, I wouldn't, this is, I agree with Petrie right here. The carrot algorithm will do the scaling for us. The carrot, and we'll see that today. The carrot algorithm is going to do the scaling for us, which is kind of interesting because in a lot of these advanced algorithms, it does some of the heavy lifting for us. So I wouldn't do that right there. Slide 20. We're gonna scaling the numeric variables should happen before converting categoricals into indicators. Interesting. Interesting. Petrie. Hmm. 1,000-point answer of the day. I'm gonna actually, Petrie just literally texted me. That was who texted me about 15, 20 minutes ago. Interesting. Because you see, he says scaling should happen there, but then go to slide 26. And I agree with him here. Carrot will automatically scale the data for us. So why are we scaling the data at all? So we will be using the Carrot package to automatically scale. Carrot has in the functions the ability to scale the data, so it'll do it for us. So that is definitely 1,000 points right there. I generally don't scale my categorical variables. They're just zeros and ones, and Carrot will handle it. So sorry for the... That is confusing, right, Sierra? I should ask Petrie. So I think that's a little bit of a contradiction right there, right? I would agree with Carrot doing it for us. So I would not go through my scaling right now. You could if you want, but I would not. Carrot's going to do it for us. Carrot is absolutely amazing. You're about to see the power of algorithms right here. We're going to be showing that today in class. Yeah, it's generally you're just getting the data nice and neat right here to something you can work with. So we are okay to change to cat and not scale before. Yeah, I'd say you're fine. It's because Carrot's going to do it for us. Like Carrot, we might just show some of that here in a second. Carrot is pretty insane. Like what we can do with ease is absolutely nuts. We're going to be showing that today in class. Last but not least, let's look for linear combos. Mainly, the big purpose of this right now is to remove out a lot of trash, to get the data to where we don't have extra stuff in it that we don't want. And the linear combos could be an issue. Propose new levels if we need it. There's my linear combos. Linear combos right here. Okay, so let's remove out the linear combos. We might not have any. Or we might have that one. I thought it would be. Let's go look for linear combos. And the answer is, whoops, wrong button. It says null. I'm surprised. Could you post this R file? Yep. In the lab, it logged them before doing everything. Do we still need to do that? Oh, well, that's a transformation. That's not scaling. So now, this is what I would do now. What I would do now is I'd transform my full data set. So now we need to run on this data set. Let's go back here. So you got to be careful because we're going to be predicting the log or probably something of demand. We need to see what happens to the Y variable of interest. So let's finish up the working on this. We're going to go to library, best normalize. And best normalize is loaded, and we'll go to best normalize. We need that code from earlier. And so we take, it can't do it on a data set, right? Yeah. Well, it might be mad about the other thing. What's the last one? There we go. Okay. So we need to do it on each vector. I wrote the for loop. In lab, it logged, yep. And there we go. Best normalize on that. Okay. And so that's the first column right there. And let's store okay. And now 5 minutes. Oh, we need to send out a message to class. Okay, so now we need to go to brain slowing down. best normalize of the vector. And there's the first column. And we want to run this. And let's store it into X for the moment so I can see the output. The output on this is X, $X. There it is, the normalized. And you want to know what was done to it, though. So to back transform this, it's going to be very important later on. We'll have to end here in a minute. Like what I plan to do, and we wrote this in a previous assignment, is to normalize the full data frame. Does that make sense, Sierra and everybody? I'm going to normalize the full data frame, but what I would do is I need to know how to untransform my Y variable of interest. So if I get predictions, I need to know how to untransform it. I need to know what is the back transformation on it, because if I'm going to make predicted values and they're transformed values, I need to untransform those Y values. So with that, we probably got to end here, but we could do more tomorrow especially. But this is just the getting started, getting our data the way we want it to look, so we can get our data in a format that works. We can get it more normalized, and then Carrot is going to do the scaling for us. Well, we'll be back here soon. We got to start class in 3 minutes. Bye for now, everyone. Bye.